so I have to etch a little longer to remove this size, this structure. So does overetch matter? Yes, because what happens if I have this structure, I etched all the green layer over here. I etched all the green layer over here, and I have this. But let's say if the selectivity of the etch rate versus of the green versus the blue is not perfect. So then I continue to etch. So what happens, I also etch a little bit here. So I can end up with two steps. This step and this step, because when I remove this green part, I also etched a little bit this part. Substrate is lost during overetch. In real life, because in real life, selectivity is not infinite. In real life, there is some finite value for selectivity. So here are the numbers here, which are describing what I just showed you into equations. So I will not go through this equation, but these values allow you to calculate how much we lose during this overetch structure. Again, we've seen this slide before, and what are the etching chemistry? The etching chemistry, we have transport of reactants, transfer of product, and the key ingredients in any wet etchant, for example, is you have oxidizers, acid or base, and dilutant material. For example, if you want to oxidize materials, we use hydrogen peroxide, nitric acid, sulfuric acid. If I want to etch, I'm using sulfuric acid, ammonium hydroxide. Basically, most basic bases and acids are good etchants. And I need a dilutant material for the transport of the reactants. I need the outcome of the product should diffuse out. So I need to give them some space. So I need to add some, we call a dilutant. You see the trade-off. If I increase the concentration, the etch rate can be very fast, but then the out diffusion will be very slow. So the overall etch will be low. So if there is some optimum concentration. If I go too high or too low, the etch rate is lower. There's some optimum deposition. For example, common dilutants are water, acetic acid, and similar material. So redox reactions. Redox reactions, etching is inherently an electrochemical process. Now, I hope you are familiar with the chemical term redox. Redox means reduction and oxidation, which means those are chemical processes which we give or take electrons as part of the process. Etching is inherently an electrochemical process. It involves electron transfer process as part of the surface reaction. The oxidation number is the net positive charge of a species. Oxidation is the process of electron loss. So we increase the oxidation number. Reduction is the process of electron gain or decrease of the oxidation number. Redox reactions are those composed of oxidation of one or more species and simultaneous reduction of others. So okay, so this is kind of a review of what you studied in electrochemistry or chemistry. Metal etch. Aluminum etch. Aluminum etchant type A. It's from Transcend Company. Now, I'm not giving, let's say this is not a commercial for any company, but I'm quoting typical etchants, and I use this in my, it's interesting, I use it in my PhD and my graduate school 30 years ago, and people still use it today. So I think I don't need to, it's not too much a publication for something that people use for 40 years. This is practically a mixture of phosphoric acid, acetic acid, and nitric acid. Etch rate is about, for 1 minute, it's about 2,000 angstrom, approximately. For multiple or metal processes, it is often necessary to etch through an insulating underlevel dielectrics. When the underlying layer is aluminum and the insulating layer is glass, the preferred etchant is like 5% BOE and 3% 3 parts glycerin, straight BOE etches aluminum. So this is just a comment. Copper. Now, if you want to etch copper, this is a wet etch. Now, this is a common etchant in PC boards, because when you deal with PC boards, printed circuit boards, you can use wet etch because it's low cost, it's highly selective, and the resolution is not a big deal because you're dealing with a line width which are in the range of 75, 100, and 125 microns. So you can allow yourself to lose few microns. So the most common material is ferric chloride or mixed etchant where you take this composition. And so these are the typical chemistry of copper etchants. And you take the ferric chloride and mix it with some other compound like sodium persulfate, etc. But the main etching here is that you have ferrum, which is iron, but this is a ferrum chloride, which means this is iron chloride. In this case, when you dissolve it in the solution, then you have ferric ions in the solution, ions of iron in the solution. If you have copper, iron and copper is a pair that the electrons prefer to go from the copper to the iron. So if you have an iron, he takes the electron from the copper, so the copper become copper ions, and then the copper dissolves in the solution. So this is a redox reaction. You are oxidizing the copper, you are reducing the iron. You're oxidizing the copper, reducing the iron. So a redox type of etching is that you're taking one material and move electrons from one material to another one, and the result is that the material that you want to etch becomes soluble. For example, copper becomes ionized, and copper 2+ is easily being dissolved in the solution. So the idea here that you need a material that, I would say it in a very simple and not very physical way, likes the electron of the copper and takes them. So the copper becomes ionized, and then it becomes soluble in the solution. So this is aluminum and copper is relatively not easy, but easy to conceive a process, easy to invent a process, because there are materials which have few possible reactions. But when you start to etch materials like platinum, for example, or gold, then things become tricky, because those are noble metals. For example, to etch platinum, you mix HCl and nitric acid and water. This is what we call aqua regia. This is, if you want to etch gold and to etch platinum, you need to have this type of processes. Otherwise, it's very difficult to etch. Chromium, I didn't even say what. You take these commercial etches, and gold. If you want to etch gold, use a gold etch. Okay, now let's talk about the electric etches. Again, you see, like this slide is like every step. We have this slide, but it's again the same picture. Now, we talked about etching metals, and I showed you that the common etchants for metal are oxidizing and etching the oxides, or redox reaction, where we convert the metal to a soluble ion and then it being dissolved. The most common the electrics in semiconductor industry are silicon oxide and silicon nitride. And silicon nitride you etch with HF. And then you can, for example, if you take 1% HF in water, you etch 600 angstrom per minute. If you take 10%, you etch about almost 9 times faster. You can mix. The problem with HF hydrofluoric acid is, first, it's very dangerous solution. Second, it attacks also photoresist. It attacks other materials. So it's very common that instead of using straight hydrofluoric acid, you mix it, for example, with ammonium fluoride, NH4F. Ammonium fluoride is soluble in water. You mix it with HF, and you have what we call buffer HF. Buffer, because it's a buffered solution. You took a salt of ammonium hydroxide and an acid, and you take a couple and you mix ammonium, in this case ammonium fluoride, with HF, and you have a solution with a lot of fluorine ions, but much less protons. So this is much less corrosive material, but still it has a very nice etching properties of oxide, and it can etch like 5 to 10 angstrom per minute, so you can do very, very controlled etching. Another way to etch nitride is use phosphoric acid, and this one etches about 100 angstrom per minute at 180 degrees Celsius. This is a little drawback. You have to heat up the phosphoric acid, but it's a common process. It gets very nice etching. Oxide etch is very simple. Buffer HF, you etch 1,000 to 2,000, 3,000 angstrom per minute. And if you use straight HF, I just put it, etches very quickly. It's just really fast. But if you sometimes, you see that people want to etch much slower, so what they do, they dilute HF. In some cases, you can find even in the companies today, they use like 100 to 1 HF in water for kind of a very, very deep etch or just cleaning process. Etch rates for both oxide and nitride vary greatly depending on film quality. This is like a big warning. If you make silicon dioxide, there are a few ways to make it. You can make it by thermal oxidation. You can make it by chemical vapor deposition. You can make it by plasma-enhanced vapor deposition. You can make it by sputtering, which I'm going to show next week. Each method you make the substrate will generate silicon dioxide, but each layer will have different etch rate. Even more, if you do a chemical vapor deposition in oxide, and you change the condition, like different temperature, different composition of the gases, the resultant oxide will have different etch rate. So the etch rate of thin films is not an absolute number, it's always the same. You need to calibrate it, you need to measure it. We know the ballpark numbers, we know the approximate values, but sometimes it can vary by a factor of 10 or even 50, so you need to calibrate it every time you have your own process. And we need to give it to you. Oxide SF, oxide etch is by HF with or without addition of ammonium fluoride. The addition of ammonium fluoride creates a buffered HF solution, also called buffer oxide H, some people call it BOE. The addition of ammonium fluoride to HF controls the pH value, and therefore replenishes the depletion of the fluoride ions, thus maintaining stable etch rate. Now, as a whole, etch rate of oxide is SiO2 plus 6HF makes H2SiF6 plus 2 water. This is soluble. Type of silicon dioxide etchant, like 49% HF. This is like a fast removal of oxide, poor photoresist adhesion, so it has a problem. Buffer HF or dilute HF. Sometimes you can have HF mixed with HCl or a hydrofluoric acid with glycerin mixture, and this is some special applications. Glycerin is organic molecule which can had some very specific effects on the surface. Why I'm showing you all this, why I'm showing you all these variations, I just want to show you that in this lecture I'm giving you kind of a general concept of etching, but the actual etching is a little bit trial and error based on the general assumptions. If you look at buffer HF solution, for example, what you see here, this is etch rate versus the bottom line is the NH4 to HF ratio, 20 to 1, 10 to 1, 7 to 1, 5 to 1. This is 25 degrees, 35, 45. What you see are two effects. First, this is the etch rate versus how much ammonium fluoride in the solution. So this is 20 to 1. You got this etch rate. The less ammonium fluoride, the higher the etch rate, which is normal. But another thing that notice here, that the higher the temperature, if you increase the temperature, you increase the etch rate, which means this is a chemical process. In most chemical processes, like most chemical reactions, you increase the temperature, you increase the reaction rate. This is just to impress you about what are the possibilities. I just took from one of the books, oxide etch rates. This is thermal oxide, chemical vapor deposition oxide, or also people call it LTO, or low temperature oxide. Some people add phosphorus into silicon dioxide. This is called phosphorus doped SiO2. Sometimes call it, some people also call it sometimes PSG, or phosphoron silicon glass. This is boron doped SiO2. So this is phosphosilicon glass. This is phosphor doped SiO2. Sorry, this is the PSG, phosphosilicon glass. And by the way, this is boron doped SiO2. You can also have boron doped glass, which is called BSG. And if you really, I didn't put it in this table, you can also mix the PSG with the boron doped. This is called BPSG. And many companies use this. Practically, you can actually mix your oxides with other oxides. Like when you take silicon dioxide and mix it with phosphorus dioxide, you have phosphorus silicon glass. By the way, why do you do it? You do it because you want to modify the properties, the physical properties. For example, the reason to put phosphorus into the glass is to reduce the glass temperature. A typical glass temperature of silicon dioxide is around 980 degrees Celsius. In some processes, you want to have a reflow. Reflow means you heat the substrate, and the oxide is like, when you put butter on a bread and put it on a hot plate, the butter spreads all over. So sometimes you want to planarize the structure, you mix it with phosphorus or with boron or with both, then the melting point and the glass temperature point goes down. So when you heat it, the glass flows and you have a very nice reflow and very flat oxide on top of it. This process was used in the 80s, in the 90s in many, many companies. Now less people use it. And what you can see that you can have here BOE, buffer oxide H, HF, HF 1%, etc., etc. Each one will give you different etch rates, and you can look at the numbers. Etch rate can vary from hundreds angstrom per minute to this etchant 23,000 angstrom per minute. Boron doped glass, the etch rate with BOE 7 to 1 is 200 angstrom per minute. So practically, you can tailor a huge range of etchant, and huge rate of etch rate depends on your substrate and the composition. I took this from the book by Madhu on processes. Etching tools, how they look. This is a holder. This is like, I would say, university-type etching systems. This is what we use in our lab. You take the wafers, put them in a cassette. A cassette is typically made of Teflon. This is a bath. You take your cassette and dip it in the bath. The bath is usually temperature controlled. And all of this is in a chemical bench or chemical hood where the air is flowing from the outside to the inside, so you will not be exposed to fumes or residues of the etching. So this is a HF bench. Silicon nitride etch, we discussed it before. Now if you want to go for kind of more professional systems, this is a hot plate or hot phosphorus bench. By the way, this is a bench, you have here a bath, you put the wafers inside the holder, you dip them inside the hot plate, hot bath. For example, to remove silicon nitride, which is a very common material in MEMS, or it was used a lot in the past in silicon manufacturing, when people used the LOCUS process, the local oxidation process. So you put oxide, you oxidize your wafer, and you have to remove the nitride. So you dip it in hot phosphoric, about 175, 180 degrees Celsius. So this is how it looks. Silicon etch. And let's talk about anisotropic etching. Anisotropic etching is a hydrofluoric, nitric, and acetic. This is what I showed you before. But bases like KOH, NaOH, EDP, which I'll give you the exact formulation, and tetramethyl ammonium hydroxide, EDP, ethylenediamine pyrocatechol etch. Those are bases, and bases are very good etchant, by the way, in general to most semiconductors, and specifically for silicon. Now, silicon, HNaH, is a mixture of nitric and hydrofluoric and acetic, as I showed you before. This is the plot, HF, acetic, and nitric acid. And you can see, for example, that if you want to etch, you want to be in this point, you can mix a mixture of 40, 30, 30, and then you can get the desired deposition rate. And practically, the nitric acid oxidizes, the HF removes the oxide. Those are the reactions. This one we discussed before. So this is the silicon etch. Hydrochloric acid, nitric acetic acid produces nearly isotropic etching of silicon. And this is the overall reaction. And etching occurs via a redox reaction allowed by the dissolution of the oxide by an acid, which acts as also as a complexing agent. Complexing means that it reacts with the silicon molecule, make it soluble. Points on the silicon surface randomly become oxidized. The nitric acid randomly oxidizes the silicon, and the HF removes it. This acts like a localized electrochemical cells sustaining corrosion current. By the way, if you look at these reactions, you know how many atoms you oxidize per second, you know the area. So you can actually measure how many electrons you remove per unit area. So you can calculate the equivalent current. So you can actually look at the from the electrochemical point of view. They act like they have a corrosion current of like 100 ampere per centimeter square. So if you look at it from electrochemical process, you have a very high local current, but this is because we etch material and the electrons are moving from one species to another, and we can look at it as a current that we oxidize and reduce these materials. Each point on the surface becomes both an anode and a cathode. Over time, if the time spent on each is the time of etching will be uniform, otherwise electron etching, selective etching will occur. So the idea is that the oxidation and the etching are random. That's why we get a very uniform. If I change this rule by putting some additives or change the surface properties, I can make it selective, but in this case we don't want it. So silicon etch. Silicon is promoted to a higher oxidation state, like silicon plus, okay, let's read it again. Silicon is promoted to a higher oxidation state as an anodic site which supply positive charge in the form of holes. So if you can think of it, you have silicon 0, it takes 2 holes to make silicon 2 plus. The NO2 from the nitric acid is simultaneously reduced at the cathode, so it becomes NO2 minus and gives 2 holes. The silicon top loss combines with OH minus to form SiO2, so SiO2 plus 2 hydroxide makes SiOH2. This SiO2 is then dissolved by HF to form a water-soluble complex, H2SiF6. So this is, previously I gave you only like 2 reactions, now I gave you 4 reactions, but still the total number of reactions is more complicated. Why I'm showing you these steps? We see that the actual chemical process involves electrons and holes in the semiconductor. This explains, by the way, why the oxidation rate can be a function of doping. This is a little different than what I'm going to show. This is oxide-based etch. What's another effect is the nitric acid has a complex behavior. Normal dissociation of water, or what we call disproportionation, HNO3 goes to NO3 minus plus H minus. Then we have an autocatalytic cycle. And I think I'll skip all this chemistry because most of you are not chemists. So if you want to look more in the chemistry, you're invited to look into this slide. But let me give you a little bit of role of acetic acid, which is very important. In many of the etchants in semiconductor, we put some organic acids. In this case, it's an acetic acid. If you're not familiar with chemistry, acetic acid, it's CH3COOH. COOH are typical, is a component which is typical to organic acids. Acetic acid is frequently substituted for water as the diluent. Acetic acid has a lower dielectric constant than water. If the electric constant of acetic acid is 6.15, water is about 81. This produces less dissociation of the nitric acid. So by putting organic acids into solutions, we change the electric properties of the solution of the electrolyte and change the electrochemical nature of the solution. So enough with chemistry. This is the total chemistry. The end of the line is they have silicon, generate silicon ions going through this process, and the end results, you start with the oxidation of silicon, reduction of the nitric, sorry, it's NO2, not NO3, as I said before. There was a typo in the slide, we need to fix it. So the result is 2 holes here, 2 holes here. Now, let me ask you a question. Since this type of etching, or also other etching, involve electrons and holes, can you recommend a way how to accelerate etching, for example? What was? Doping. Another way, if I don't have doping and I want to accelerate, or current, but if I cannot touch the wafer, I cannot supply current, what? What? Let's say I don't have a power supply, I'm in the middle of the island, there's a lot of sun but no electric fields. Light. I illuminate. If I illuminate the substrates, I can generate electrons and holes. They can also modify etching rates. So why I'm saying this, be careful. When you do etching of silicon and other semiconductors, you have to remember that sometimes etching in dark and etching at light can be different and may explain some variations in your experiments. Sometimes you can accelerate etching by illumination. And this is, by the way, called photochemical etching. Some processes you can induce etching only on the spots that you illuminate. So you can even do direct printing using this kind of etching, and some people use it in some processes. The main problem of photo-induced etching is the resolution depends on the light of the wavelengths of the light, so you cannot etch with a resolution less than a few microns. But if you have a larger features, and you can use photo-induced etching. Now, let's talk about silicon crystals. Silicon crystal is a diamond structure. You took 2 FCC structures and you mix them together, so you have every point of silicon is connected to 4 other atoms, so the silicon is like in the center of a tetrahedra. So we can define the unit cell, the smallest volume segments representing the entire lattice. And we have the basis vectors. We can define each unit cell can be translated in the lattice by integral multiples of the basis vectors. And the silicon lattice is practically a diamond lattice. Atoms with 4 covalent bonds. So if you look at the silicon structures, recall that crystal lattice is in a face-centered cubic with 2 atoms basis that you have atoms also at the 0, 0, and the 1 over 4, 1 over 4, 1 over 4 in every corner. So this is the 1, 0, 0 structure, it's the 1, 1, 0, sorry, this is the 1, 0, 0 plane, 1, 1, 1, 0 plane, and 1, 1, 1 plane, as you studied in other classes. But if I look at the density, how many atoms I have per unit area, and if you do the calculation, you find out that 1, 1, 1 is the densest plane. If you calculate how many atoms we have per unit area on the 1, 1, 1, you got a denser concentration or different concentration than the 1, 0, 0 or 1, 1, 0. I don't know, this slide is from a different place. Okay, so this is the crystallographic etching. This slide I already showed you. So it's kind of in the wrong place. So if you have this diamond structure in your mind, and you have differing hybridized orbital orientation, because in a silicon structure you have the sp3 hybridization. And because of this, the orbital orientation on different crystals plane causes drastic differences in H rate. In silicon, H rate on 100 is faster than 110, faster than 111. Remember, in silicon, top and bottom surface are the same because it's completely symmetrical. But the H rate on the 110 is less than 100, but much faster than 111. The 111 family of crystallographic planes are normally the stop planes, because along the 111 planes, the H rate is very, if this is the 111 plane, the H rate is defined in perpendicular to the plane. Along the 111, it's very small. Along the 100, the H rate is very fast. So if the H rate into the 111 is very, very small, and the H rate down is very, very fast, on the 100 surfaces, we got some very interesting features. For example, let's take a 100 wafer. Now, just a definition, 100 wafer is a wafer where the vector perpendicular to the surface is in the 100 direction. But because the 100 direction and the 1010, because this is a cube, the cube has 6 planes on the 100, 010, and 011, 1 positive, 1 negative. So every cube has 6 planes. So this plane is 100. So what we do now, on this gray silicon, we put mask, and then we etch. What happens is the following. We start to etch downwards. So the etching is very fast. But we have also a 111 plane in this direction. So what happens, along this plane, there is no etching, or very, very slow. So what happens, we etch down, but there is no etching perpendicular to the 111. So what we are doing, we are practically etching in parallel to the 111. So what we have this sloped structure, where the angle here is 54.74 degrees if you do some geometry of a crystal lattice of silicon. This is the angle between the 111 and the 100 planes. Now what happens if I have a very small feature? I etch from here, and then the etch stops. This is called a V-groove with an angle of 54 degrees, and the etch stops, and the process stops by itself. It's a nice process. Now what happens if I have a 110? On a 110, I can have the 111 can be in this direction or in this direction. So I can etch like downwards for a while, and then I can get this type of features. And if I have very narrow structures, I will have this. So I can have here very, very anisotropic features. Now it's even more complicated because it depends not only on the vertical dimension, it depends how I put the mask. For example, if I have a square hole, from one side I etch in 54, and other side I etch in 54, but I etch in 54 degrees from the top and the bottom. So what I will have is like a like a square pyramid on the opposite etched inside, and it will look like this. What are the sides? What happens? This plane here is in 54 degrees. This is in 54 degrees. So you can calculate. You can use some simple geometry to calculate the depth of the pit. I don't know by heart, but if it's close to, by the way, we use the fact that 54 is close to 45, so we can assume that it's almost the depth is these triangles are they are kind of easy to calculate them because if you assume it's 45 degrees, and then you can modify it, or just use simple geometry to calculate because you know this angle. You know this angle, so you know that the depth divided by this distance is like you can do depth divided by half the distance will give you tangents of 54 degrees, so you can calculate the shape. Now what happens if you have like an L shape, or not L, like this kind of structure? What you will have two V grooves, but on the top you have a little bit of this kind of a plane. It's not going directly deep inside. Now, if you oops. Depends on the width of the top and the time of the etch. What happens if you take this structure and then you etch on the sides? What happens is that you got some etching also from the corners. That's why you etch under. So what you can do, you take this pattern and keep it for some longer time, and what happens, you etch all the silicon under this beam, and you end up with an overhang structure. This is a wonderful way to make MEMS device without actually etching any specific process. You use the fact that you also etch under. Now, by the way, if you take this very awkward mask, you can end up with this kind of a structure. So you can make a beam like this. So you can have very interesting structures. And by the way, sometimes it's not so trivial to predict what you're going to get after the etching, because you are etching in 3 dimensions, and every dimension depends on the slope, on the crystalline plane. For example, let's say we have a 100 silicon wafer, and we have this structure. If I etch normally, this is what I get. I get from one side like this, and then 2 from the side. But what happens if I rotate this? If I rotate it, I still will get a square, but much wider. Which means that if I have my wafer and I line it correctly, then I get one side. But if I rotate the wafer, the results will be different. So when you do anisotropic etching on silicon, it's not enough to align the 100 here. You need also to align the wafer to be in the 100 and the 100. You need to align all the 3 dimensions. So hydroxide etching of silicon. Now the etchants which give this wonderful anisotropic etching are KOH, NaOH, cerium hydroxide, rubidium hydroxide, ammonium hydroxide, tetramethylammonium hydroxide, all this hydroxide. And these are the chemical reactions. And practically, this is a better slide. I put a few slides. This is silicon etching in an alkaline solution, which is typically at an oxidation stage. Silicon plus 2H2 make this silicon hydroxide. And then we have the reduction stage where we're reducing the water to hydroxide. And the main reactants of the etchants are water molecules and the hydroxide ions. OH believed to be provided by the water near the silicon surface. Reduction of water believed to be the rate-determined step. The overall gross silicon oxidation and reduction is like silicon plus 2 hydroxides plus water. You make this material which is soluble. I will skip this slide. This practically I put here some qualitative models, but this is a reference. I will not cover this in the class. If you want to learn more about the solution of silicon using this type of material, I put these slides. But this is how it looks. This is a real life. You start with the mask on top, and this is the etching under the mask. And you can see that this is the mask, probably protected by either silicon nitride or gold. If you want a material that is not etched by KOH, for example, you can use gold. Gold is a nice material. You can also use silicon nitride because it's not much fast etched by KOH. Now what happens here, this is very narrow, so you have a complete undercut. And what happens, you see at the bottom, it's a little difficult to see, but you see that this center is still, there is a pedestal under. There's some silicon material under it, which is kind of holding it in the center. And again, if you Google silicon etch by KOH, you can see wonderful pictures. And this is also KOH of silicon. And this is the angle here is 54 degrees approximately. And here we get here we put some protective mask on top of it. This is the mask on top of it. This is how it looks. It's pretty nice. And this is KOH of silicon. This is what I showed you before. This is the mask around. This is the etching. And by the way, this is a wonderful way to make a nozzle. Because if the silicon is very, very thin, what happens? You define this mask, and you etch in this angle, and etch in this angle. And what happens if you reach the bottom of the silicon wafer, and there's no silicon? So what you end up with a hole. So this was the first technique that people used to make inkjet printers, because you can etch silicon, you get beautiful, well-defined nozzles in silicon. And practically, the way to make nozzles for inkjet, and one of the known techniques today make nozzles for inkjets, is to use silicon etching this way, because it's a very simple process, very reproducible process, and you can make very well-defined nozzles. And this will be the volume where you keep the ink, or also do some other processes. This is another KOH of silicon. This is like kind of a square shape. And you end up also with kind of a window on the top. And this is, sorry?
What kind of other applications?
You tell me. The question was what kind of applications. There are many applications. All of them belong to the field of micromachining. This is a way to micromachine silicon. You can make nozzles. You can make microfluidic system to control flow of liquids. You can make pumps, micropumps. It's used in drug delivery. It's used in biochips. It's used in the car industry. You can make injectors. You can make accelerometers, because if this is a membrane, for example, you put on top a membrane, the pressure on the membrane, you can sense it on the fluid on the other side. Or you can use it to make accelerometers, like this beam that I showed you before. This beam has a mass. So when you accelerate, the beam will move connected to a capacitor, and you can measure the capacitance. The capacitance will be a function. So if you look at your cell phone today, and you have, how do you know the cell phone is tilted? This is made by micromachining. So, and KOH etching of silicon is one of the oldest and most used processes to etch silicon at very low cost, at very accurate way. Although today a lot of people switch to dry etching because dry etching is more accurate and the prices are reasonable. But wet etches are also very widely used. And as I showed you before, you can have these structures and etch V-grooves, tunnels. You can combine them or make a complete floating structures. This is, for example, what you can make. This is a small mask, larger, larger, and larger. And you can see that what happens is that you can make like a beam. This is called cantilevers. And the beams can be supported. You can make them like this way. You can make them this way. You can make, for example, this structure. This is like a spring. And you know that every spring has a resonating frequency. You can use it for applications where you use the resonance properties of these materials. Or if you really want to make it crazy, this is another structure. You can make kind of a really interesting springs. Springs are used for accelerometers, because if a mass connected to a spring, you measure the deflection of the mass is proportional to acceleration, because this is Newton's law, F equal m times a. And the force is equal k times x. So if you measure x, you can measure acceleration if you know the spring constant. So this is bulk micromachining. And these are the typical reactions, KOH, and these are the etch rates. The hardware is very simple. You can use a hot plate and a simple system. Presence of alkali metals makes this completely incompatible with MOS and CMOS. So this process, as I showed you before, the etch rates, again, you add isopropyl alcohol so you can get these structures, as I showed you before. A typical silicon etch rate depends on the KOH concentration. The higher the concentration, look at the etch rate. The etch rate